So we've seen the one-point compactification, but this is really useful provided the space is locally compact, that is small regions are compact, and it's housed off. And well, let's just define this definition. So X is a topological space. Definition: X is locally compact if every point in it, X in X, has a neighborhood, which means an open set containing it, V, such that, well, V itself can't be compact, but it's open, and compact sets are usually closed, but such that its closure is compact. Okay, and of course the basic example is Rn is locally compact. So anything locally like Rn is locally compact. So we have plenty of such examples. So by the way, an example, I'm going to call this an exercise, is R2 with, of course, usual metric is locally compact, but the essence of metric is not locally compact. Good exercise in understanding definitions, because these different rays, even though they're next to each other in R2, metrically they're far from each other. So a metric ball will include lots of disjoint lines, and if you take things at a fixed distance, so you take any metric ball around the origin, open set contains such a thing, and take the boundary of this, that will be discrete. Okay, so this is, that is to say, boundary as the, if I look at X in R2, and distance between x0 is whatever fixed number, epsilon, is discrete for epsilon greater than 0. It's discrete and infinite, so it's impossible inside a compact set, because in a compact set you must have accumulation points. This discrete set has no, so it also has no accumulation points, but in any case it's closed, etc. So this was an example which is not locally compact. And now what does local compactness give us? The theorem is that, well, if it is Hausdorff also, if X is locally compact in Hausdorff, I should have called this a lemma. It's not so useful in itself, but for a theorem that will follow in Hausdorff, then X star is Hausdorff. And the converse is also true. Okay, so if we have proof is that given xy in X star, if x and y both belong to, so of course x is not equal to y, so both can't be infinity. If x, y belong to x, then follows there exists u, v, so and so as X is Hausdorff. Open sets in X are also in Hausdorff. Okay, and if y equals infinity, say, so if one of them is infinity, say y, then there exists K compact, which implies closed, because the space is Hausdorff, such that, oh, sorry, I don't want V here. Take V as in definition of local compactness. So once we take this as in the definition of compactness, that is V bar is compact, then V and X minus V bar are disjoint neighborhoods of X and infinity, and Y equals infinity. We did not actually use Hausdorff here, except that we used it in defining X star. and proving that we had a topology on X star. So you could try to play this argument exactly the same way, dropping the Hausdorff condition, except that your X star will not be a topology. So you'll get a sort of formally similar looking statement, but which would be nonsensical because it's not a topology at all. Okay, so what we know is Fx locally compact in Hausdorff, then X star is Hausdorff, and X star we have seen is always compact. Yeah, that is because, well, as I said, we have seen, I forgot that we actually have not seen that X star is compact. So let me note, this is of course a theorem. This does not have to do with local compactness. X star is compact. Let's prove this. Okay, so this is crucial in what follows. So let U alpha be an open cover for X star. Okay, then infinity is contained in so infinity of X is contained in U alpha naught for some alpha naught. Okay, so as U alpha naught is open, so we know what are the open sets containing infinity. Hence U alpha naught is going to be X star minus C. Okay, hence, no, not hence, so we know this. So now if we just drop U alpha naught, so the sets U alpha intersection X form an open cover, or even with C, form an open cover for C. So C is contained in some finite subcover, which is C is, unfortunately, I'm going to call this K because my C and inclusion look too much like each other. So they form an open cover for K. So this is X star minus K. So K is contained in U alpha 1 union U alpha n. Okay, so X star is contained in, just by set inclusion, U alpha naught union U alpha 1 union U alpha n. So this is the required finite subcover. So this is always compact whether or not the space is Hausdorff. The space is defined to be Hausdorff. X star is compact. We always have an embedding of X in X star. Okay, and now we also saw that if X is locally compact in Hausdorff, then X star is Hausdorff. Okay, so this will give us the basic properties of locally compact spaces. Now to make good use of this, we need another notion, which is that of a proper map. To motivate this, recall the example we had where we had a bijection which was not a homeomorphism. It sent a half open interval into a circle. The thing is that an infinity went to a finite point. So proper map is one where infinity goes to infinity, and the cleanest way of defining it is that f from x to y, let's say assume it's continuous, is proper if for all k contained in Y compact, f inverse of k is compact. Okay, what does this have to do with compactness? Well, specifically remark, if x and y are compact, in fact we'll see we need it for only one of them, compact Hausdorff, we need less than this, then every continuous map is proper. Actually, we just need x is compact and y is Hausdorff, because if k is a compact subset of y, then it's closed. So because of continuity, its inverse image is closed, and since x is compact, it follows that it's compact. So if we are talking about maps from a compact space to a Hausdorff space, It's better, let me just say it correctly because that was our hypothesis earlier. So if X is compact, it has no infinity in a sense, and Y is Hausdorff, then every continuous map is proper. So this is justifies in some sense how you say it. And exiting infinity is going to infinity is exiting all compact sets. I mentioned Freudenthal compactification and so on, which use this very well. I mean, there are many ways in which you use this very well. Okay. So now we can. So we have X star. So now we have a following situation. Suppose F maps X star. Oh. Now suppose we have X and Y is a map. Since I want to state a theorem, the next page we'll ask, so when does F extend continuously to X star to Y star? I might as well call this F star. Well, actually in this case it does, but we want to actually send infinity to infinity. We want a canonical extension such that F star of infinity X equals infinity Y. Okay. So that question can be answered in the following theorem. So let F star, so let F from X to Y be continuous. And then define F star mapping X star to Y star by F of X equals F star of X equals F of X for X in the space X, and F star of the infinity of X is the infinity of Y. Okay, so this defines a function. Then F star is continuous if and only if F is proper. Okay. So the proof is, first we want to show continuity at all points. So I'll just say easy to see what I have resisted in this course, but this is really easy to see, so you can take it as an exercise. F star is continuous at X in X. At X, let me put it this way, for all X in X, as F is continuous. Anyway, even though I said easy to see, let's see it a bit. So here we have X and we have the infinity point. I've put it far away, it won't be far away. And then here we have Y, but and another infinity point. And so we have this point X here, and then I have F of X. And I have an open set containing Y. It may or may not contain infinity, but we saw that if our space is Hausdorff, we can pass to a smaller open set by dropping infinity. It will still be open if we look at X intersection these sets. So we have an open set which is open in Y, and continuity of S tells us there's an open set which goes here. Okay. So how about being continuous at infinity? If F is proper, any neighborhood of infinity is X star minus K, where K is contained in X, is compact. So we see that if I look at, it's Y star, any neighborhood of infinity, I didn't say which one, Y, I want to look at the image here. So infinity X goes to infinity Y. So if F is proper, we want to check continuity at infinity, that is infinity X going to infinity Y. Any neighborhood of infinity Y is Y star minus K, where K is compact. We see that if I look at X star minus F inverse of K is a neighborhood of infinity such that F star of X star minus F inverse of K This by definition is contained in y star minus k. Okay, so thus continuous at infinity. So infinity x, and we can see the converse also. Conversely, if we have a f, so conversely, suppose f star is continuous. We want to show it's proper, right? Map is proper, and k is contained in y is compact. We need to show f inverse of k is compact. Okay. Then what we know is that y star minus k is a neighborhood of infinity. So hence there exists some L compact, L in X, such that if I look at the image of this neighborhood, so there is some neighborhood of infinity in X, but that must be of this form. This is contained in y star minus k. Okay, so hence f inverse of k is contained in L. So anything outside L goes outside k. So anything that goes into k must be in L. Okay, so is a closed subset because f inverse of k is closed. K is compact, so it's closed. Everything is Hausdorff around here. So it's a closed subset of a compact set, which is L. Hence compact. Okay, so we have done the work now. What we have seen is that if these are locally compact Hausdorff spaces, then we have an induced map if and only if the map is proper. Okay, so this lets us generalize. One can refine this and say when maps are closed, but let me just save time by just having a generic statement. So the generic statement for a similar proof will work in a more refined case. If X is Hausdorff and Y is locally compact Hausdorff, notice I dropped the compactness from X. Previously X had no hypothesis. We throw in that it's Hausdorff. Previously Y was Hausdorff, but now we require it to be locally compact Hausdorff. Then any map, well, let me state it in the strong form. Any proper continuous map. So proper includes continuous. So let me just say any proper map f from X to Y is closed. So of course the idea of proof is that f extends to f star mapping X star. This is compact to Y star, and because of locally compact, this is Hausdorff. Compact, this is Hausdorff. Okay, the local compactness was necessary to make this Hausdorff f star. Okay, which is a closed map. Recall the reason is that any closed subset of the compact space is compact, so its image is compact, and in a Hausdorff space it's closed, which is a closed map. Okay, and now we also know that X is a topological embedding in X star. So if f contained in X is closed, then f equals X intersection f star closed in X star, because it's a topological embedding, the inclusion, so X has the subspace topology. So the X f star is closed in X star. So f of f, which is going to be Y intersection little f of f star, because infinity goes to infinity, so this is closed in Y. We once more use the fact that the subspace topology on Y coincides with the original topology of Y. Subspace is a subspace of the compactification. Okay, so this is a very useful result. It lets us show homeomorphisms. It in fact characterizes it, so you can see positively and negatively. If infinity goes to a finite point, it need not be a homeomorphism. If infinities go to infinities, that's proper map, then we have a homeomorphism.